10:10. Let's get started. So, hello everyone. Thank you so much for attending the tutorial once again. So just first a couple of announcements. So we'll be having our midterm for the course next Monday during the regular lecture hour, which is 1 p.m. So the midterm will last around 90 minutes. Yeah. Let me put it here. 19 minutes, roughly. So our current plan is for it to last for 90 minutes. And the midterm will take on the form of a quiz on Quarkers. We will be using the lecture Zoom link that we used for regular lectures for live Q&A for the midterm. Okay, so what will happen is that we'll be joining the lecture Zoom link to answer your questions. So in case you have any questions or concerns regarding the midterm. And what you have to do for preparation of the midterm is that there will be probably some questions that ask you to upload like certain graphs, for example. As an example, so the questions might ask you to draw a control flow graph, etc. So yeah, so what you want to prepare for the midterm is you want to prepare for a file upload onto Quarkers, okay? Or let's say, for example, you write something down and you take a picture of it and you upload it to your computer. Okay, so prepare for file upload questions. And finally, so the midterm will cover everything that we have discussed during the lectures and tutorials, but there is no question on loop invariant code motion and register allocation. Okay, all right. Any questions? So yeah, we'll be covering register allocations in the lecture this afternoon. Any questions or concerns? So there will be questions that ask you to write high-level pseudocode, but there won't be like questions that require you to write C++. Any other questions or concerns? Okay, so if there are no questions, let us go to the topic that we'll be discussing today. So in today's tutorial, we'll be discussing about lazy code motion. Okay. So the first question we want to ask is, what is lazy code motion? So let me try to answer this on the board. Has everyone copied this down? Can I erase this? The goal of lazy code motion, as we will be seeing in this tutorial, is to eliminate partial redundancy with we said that so the goal of lazy code motion is to eliminate partial redundancy with minimum register usage. Okay, so what does this mean? and we'll be seeing this, and we'll be again discuss about this once we finish covering all the materials in this tutorial. Hopefully, everyone still remembers what we described previously when we cover available expressions. So what makes partial redundancy different from global redundancy? Well, as we can see from the control flow graph on the slide, in the case of partial redundancy, the expression is only redundant on one of the program passes, but not all. As we can see here, so the expression a plus b is evaluated twice on the left-hand side of the program pass, but not on the right-hand side. So this therefore makes it different from global redundancy, because in global redundancy, we'll be evaluating the expression a plus b on both sides. So therefore, how should we eliminate the partial redundancy? Well, a naive solution for this problem will therefore be simply insert an extra expression, let's say x equals to a plus b on the right-hand side, and apply everything that we have for global redundancy elimination. So is this approach going to work? Well, let us consider a simple control flow graph here. As we can see, so this control flow graph is kind of similar to what we had previously, right? So we have expression a plus b evaluated twice on the left-hand side. Therefore, the question becomes, can we insert the expression a plus b on the right-hand side, which is the basic block as is shown here, and apply the global redundancy elimination process like we did before? The answer is no. So why is this? So let us consider the control flow graph that we have here. Where we have an extra instruction, x equals to a plus b, inserted on the right-hand side of the basic block. So what do we notice here? Let us assume, let me draw this on the board instead. Currently, we have expression a plus b evaluated twice along this program path. To avoid such redundancy, the solution that we propose would therefore be insert an extra expression a plus b here, so that we can apply whatever we have previously in the case of global redundancy elimination. So what's wrong with this approach? Let us assume that the program, instead of taking this path or this path, takes this path at runtime. So let us assume that the program takes this path at runtime. So what will happen? We observe that assuming that the program takes this path at runtime, they will have to evaluate the expression a plus b, which is a redundant compute on this program path, right? Because in the previous case, we're in the baseline, without any optimization, the program does not have to evaluate the expression a plus b when taking on this path. right? Therefore, what we observe is that so after the optimization, the performance when the program takes this path actually becomes worse. Why? The reason is because so it has to you does an extra evaluation for this expression a plus b. Does everyone get that? And to make matters worse, assuming that so the expression is not a plus b here, but let's say the expression is something like a divided by b. And further assume that so the condition we have here is something like b is equal to 0 or not. So if it is equal to 0, we'll go to this side. If it is not equal to 0, we'll go to this side. So therefore, yeah, similarly, if the expression that we have is not a plus b, but a divided by b instead. So what we have here. So by bringing the expression a divided by b here, we introduce this extra computation that is not valid, right? Because it is possible for b to take on the value 0 here. And if it indeed takes on the value 0, in the baseline, this won't be a problem here, right? Because the control flow graph avoids the case when to evaluate this expression a divided by b when b is not equal to 0. However, if we apply the naive solution that we had previously, which is to put the expression a divided by b here, we bring in this computation that is not valid at this program point. Therefore, causing unexpected program behavior. Any questions so far?
Just quick question, actually.
Yes, please.
So I guess you would just look at the computation that's happening, and then check if the variables are being used anywhere else in that block after that point. And if they are, then you can't do the partial redundancy, right?
Sorry, could you please repeat?
So like basically you check the computation that's happening, like a divided by b or a times b, and then you check if any of those variables like a or b are being used after that computation. And if that's the case, then we don't do partial redundancy, just like in this case. Because if b was before, if b is equal to 0 was above a divided by b, then you could technically
it has nothing to do with computation. So as we have described, so even if this is not a division, this is a plus, so we will still experience problem. The reason is because, so if this is a plus here, so what we observe is that so the performance along this program path is worse, right? And we do not want any optimization to make our program performance become worse.
Okay.
So yeah, it has nothing. It's not related to the. It's not related to the actual computations that we are doing.
Okay, but if the b equals to 0, if b equals to 0 was in the above block, then we can move it, right?
No, I mean it has nothing to do with this block. Like even if let's say it is not b equals to 0, we still cannot do it. We still cannot put naively put the expression a plus b here, because this makes the performance along this program path becomes worse.
Okay, but it wouldn't break at this point.
Yeah, it wouldn't break, but it just makes it.
Okay.
What I want to show here is that so it can lead to like even worse situations that might even break your program. But I mean,
okay.
the general case, its performance becomes worse, which is also something that we do not want.
Yep, gotcha.
Any other questions? The reason that makes this happen is because the expression a plus b is not anticipated on the rightmost program path. So what does it mean to be anticipated? Well, we say that so an expression as anticipated at program point P, if all passes leading from the current program point to the exit eventually evaluate the expression using the value of each operands that are available at that program point. So this definition is sort of complicated. But can anyone please tell me, based on this problem formulation, that if let's say we are about to formulate this problem as a data flow analysis problem, what do you think shall be the meet operator of this data flow analysis problem? Anyone? Any ideas? Like, what do you think shall be the meet operator in this case? So how do we, so why do we say that, so the meet operator in the case of available expressions is intersection? Why is that? Is it that, is it? So one of your colleagues says, yes. So what do you think shall be the meet operator in this case? Yes, exactly. So why is that? So your colleague answers the first question, which is the meet operator and direction. So why is the meet operator intersection? Well, clearly we can see from the problem formulation that so the formulation requires that the expression is anticipated if all passes from the current program point to the exit eventually evaluated the expression. Since we are considering from the current program path up until the exit rather than from the entry up until the current program path. So therefore, the analysis direction that we'll be using should be backward analysis. Okay. Any questions here? Again, so the reason for the intersection meet operator is because so the problem formulation requires all program passes. And the reason why it is backward analysis is because so we are looking actually from the exit up until the current program point. Okay. So therefore, the meet operator in this case is intersection, whereas the direction of analysis is backward. Any questions here before we move on? So let me just switch back to the whiteboard and thus the anticipated expression analysis here. So assume that, so let us go back to what we have. So assume that we have expression a plus b here, expression a plus b here. So let's now do a backward analysis by looking from the exit up until the current program point here. Because the expression a plus b is not evaluated in this region. So therefore, it is not anticipated in this region. Okay. And starting from here, because the expression a plus b is evaluated, expression a plus b becomes anticipated starting from this program path, starting from this program point onwards. So I use the green edge to denote anticipated and use the black edge to denote not anticipated. Okay. So expression a plus b becomes anticipated here. And from this point onward. But what about this program path? Well, in this program path, because the expression a plus b is not evaluated here, it is not anticipated along this program path. Okay, and as we pass through this basic block, it's still not anticipated. As we reach here, hopefully everyone still remembers from our data flow analysis framework, we'll be applying the meet operator. Because we said that, so from the problem formulation, the meet operator in this case is the intersection. Therefore, after applying the meet operator, we can see that expression a plus b is not anticipated from this point onwards. Okay. Does anyone have any questions regarding the anticipated expression data flow analysis? Therefore, what we observe is that the expression a plus b is not anticipated at this region. Therefore, this also means that it is not safe to directly insert the expression a plus b here because it is not anticipated. Any questions? Okay, so if there are no questions, I will move on. So yeah, this is just exactly the same as what we draw on the whiteboard. Okay. So therefore, so the question now therefore becomes, so since we know that expression a plus b cannot be naively inserted on the rightmost program path, does this just mean that the partial redundancy cannot be eliminated at all in this case? Well, the answer is no. We can do a simple transformation of the program to make partial redundancy elimination possible. So how do we do that? Our observation is that so there is one edge of the control flow graph that is giving us trouble here. So which edge is it? We observe that it is the edge in the middle that is giving us trouble. Why is that? Because it sort of connects the region where a plus b is anticipated and the region is not, right? If we could have like some region in between, some region in between, that region will still have expression a plus b as anticipated. So therefore, we are safe to insert the expression a plus b here. We define the edge at the middle as the critical edge. Okay, so we define critical edge as an edge that whose source has multiple successors. As we can see here, the edge, so the edge here, for the edge here, its source has multiple successors. Okay, whereas its destination has multiple predecessors. Because as we can see here, the destination has multiple predecessors. By breaking the critical edge here, which is to insert a synthetic block at the middle, we can therefore have a region of A plus B, where A plus B is anticipated. And hence, we can apply whatever we have previously for global redundancy elimination to remove the partial redundancy in this case. So therefore, this is the very first step of our lazy code motion, which is to remove the critical edge by inserting synthetic blocks. And the next step we'll be doing is to do anticipated expression analysis. So let me just mark it here. First, the critical edge. Step number 2, anticipated expression analysis. Any questions here? Any questions so far? So if there are no questions, let us consider an example here, a similar example here. Sorry, not a similar example, but an example here of anticipated expression. So can anyone please tell me what the anticipated region is? So clearly, similar to what we did previously. So we start from the program exit and we keep moving forward until we reach expression A plus B, because expression A plus B is evaluated, therefore it is anticipated. And until we reach the A equals to 10 on the rightmost path. Because starting from A equals to 10 onwards, we are no longer evaluating the expression A plus B using the value of A and B that is available at that program point. Therefore, expression A plus B is no longer anticipated from that program point onwards. So to conclude, the final anticipated expression analysis looks like this, where we have the green region as the where we have the green region as A plus B is anticipated, and the red region as A plus B is not. So what is the anticipation frontier in this case? We said that so the anticipation frontier is the places where the expression where the anticipation transits from 1 to 0. Therefore, what is the anticipation frontier in this case? Well, we said that the anticipation frontier is like this, where we have this and here. That is the anticipation frontier in this case. Again, so the anticipation frontier looks like this. Based on the anticipation frontier, we can therefore simply insert the expressions at the anticipation frontier to make partial redundancy global. right? As we can see here. So if we insert the expression a plus b at every anticipation frontier here, 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 and here, we can therefore make this partial redundancy global, right? And again, so we can apply whatever we have previously in the case of global redundancy elimination and eliminate the partial redundancy a plus b along this program path or this program path, like our program paths that we have. Okay. However, so this is just another example on anticipated expression. So let me go through this quickly, and you are also free to go through this at home. So the point I'm trying to make here is that, so let us consider this example. Again, so what is the anticipation frontier in this case? Again, so recall that the definition of anticipation frontier says that, so anticipation frontier is the place where the anticipation transits from 1 to 0. Okay, so what is the anticipation frontier in this case? Well, we said that the anticipation frontier in this case is here, which is after after a equals to 10, and here in this basic block. Okay, so those are the two places for the anticipation frontier. But what do we further notice? Do we really need to insert the expression a plus b at every anticipation frontier that we have? What we observe in this case, that the expression a plus b, although the expression a plus b is killed, so hopefully everyone still remembers the definition of gen and q from available expressions. So although the expression a plus b is killed on the left program path, which is here, because we set a is equals to 10, which kills the expression a plus b. It is not killed on the right, along the right program path, right? Although it is no longer anticipated there. Therefore, what we want for the anticipation frontier is that, so we want to filter out in the anticipation frontier the program points where the expression is not killed. Again, so we want to filter out in the anticipation frontier the program points where the expression is not killed. Okay, this therefore we need our second step, which is called will be available. Will be available data flow analysis problem. So we said that an expression a plus b will be available at a program point p if all passes leading to p anticipated the expression but not subsequently kill the expression. Again, what is the meet operator in this case, and also the direction of analysis? From this problem formulation. Anyone? Hopefully this is similar to what we described before. Well, yeah. Hopefully this is not too hard based on the questions that we have practiced before. Anyone? So based on this problem formulation, what shall be the meet operator and direction of analysis? Anyone? I mean, you guys, you answered. So what is the meter operator and direction for anticipated expression? So how is it different in this case? What do you think shall be the meter operator and direction of analysis in this case? Or if anyone has any questions regarding what we have discussed previously, feel free to ask as well. Anyone? So the meter operator in this case is still intersection. Why is that? The reason is because so based on the problem formulation, it is still all program passes leading from the entry to until the current program point. Okay, because we are looking starting from the program entry. Therefore, the directions of analysis in this case is forward rather than backward. And the transfer function, as we said, the reason is because there will be available expressions. Looks at the expression as anticipated, but not subsequently killed. So therefore, its transfer function is given by anticipated minus the Q. Okay. Let us consider back the examples that we had previously on the previous slide, where we use the green region to mark the part where expression a plus b is anticipated, and the red to mark it is not. Okay. So let us consider the will be available expressions, where we use the yellow region to mark the places where the a plus b is will be available, but use the purple region to mark the places where it's not. Okay. As we have described previously, the transfer function of will be available is given by anticipated minus q. Now let us take another look, take a look at the right program passes once again. Okay. We observe that although the expression, there is an anticipation frontier for a plus b on the right program path. Okay. That anticipation frontier is, however, filtered out if we perform will be available expression analysis. The reason is because the expression a plus b is not subsequently killed on the right program path. Okay, so whereas on the left program path, we have an anticipation frontier for a plus b here after setting a is equals to 10. It is not will be available, okay, because it is marked as, because we have a equals to 10 that kills the expression a plus b. Therefore, it is not will be available in this case. Based on what we have for anticipated expression and will be available expression, we therefore define what we call the earliest placement, which we said that the earliest placement is defined as places where the expression is anticipated but not will be available. Any questions here? I mean, if you have any questions, please ask now, because you anyone needs to deal with it in your assignment. Is this clear to everyone? What the earliest placement means? So therefore, in the control flow graph that we are showing on the slide, we'll be having one earliest placement on the left-hand side of the program path. Okay, which is here, after setting A is equals to 10 here. Any questions for earliest placement or anything that we have discussed previously? Anyone? So now that we have what we described previously is to eliminate partial redundancy here, which, as we described, is the first half of the definition for lazy code motion. But what about the second half? What does it mean to eliminate partial redundancy with minimum register usage? Let us consider a simple example of partial redundancy elimination that we had at the very beginning of this tutorial. Okay, where we have let us consider back this partial redundancy, simple partial redundancy example that we had at the very beginning of this tutorial. Based on this example, I now have two solutions to solve for this partial redundancy. For solution number one, I propose to insert the expression A plus B here. And therefore replace the evaluation of A plus B and A plus B here with the value T. As another solution, as an alternative solution, I propose to, so and this is evaluated to T. T is equals to A plus B, T is equals to A plus B, and T is equals to A plus B. And we replace the A plus B here with T. As an alternative solution, I propose to insert expression A plus B here and to replace the expression A plus B here with T. Which solution, which one of those two solutions do you think is a better one? Anyone? Which solution here do you think is a better one to solve the partial redundancy elimination problem? Well, let me argue for the solution on the right-hand side. Why is it? Let us consider the register lifetime for the registered key in this case. Okay. Consider the register lifetime on the left-hand side. What do we see? So the T, which is defined here, has to be live throughout the entire program. Okay, so this is basically the live range for T. Yes, so yeah, to answer, hopefully we are seeing the same left and right. So yeah, this one, let me just say this one is better to avoid any confusion because I'm not sure whether you are seeing. This one is better. So yeah, back to the explanation. The reason is because to consider the live range for T. So T is defined here, and it needs to sit in the register file throughout this program until this program point here. But what about in this case? We observe that the live range for T in this case is given by here. Clearly, the lifetime for T here is shorter. We prefer register with shorter lifetime, right? Because hopefully everyone still remembers what we learned from the computer organization course, that register is the most valuable resources, like one of the most valuable resources, our CPU, right? And therefore we want to minimum register life usage or lifetime. And we want this variable T to live as short as possible, right? Because we need to reserve space for the other values, for other computations. So therefore, to conclude, the solution T, this one, is more preferred. The reason is because the register key here has shorter lifetime. Is this clear to everyone? What it means for minimum register usage. This is important to understand the second half of lazy code motion. So if you have any questions, please ask now.
Sorry, I had a quick question.
Yes.
When we started the tutorial or even the lecture slide, didn't it say that you want to have as little occurrences of the expression a plus b?
But
so
okay, so I see what you mean here. So you are concerned that the expression a plus b occurs twice in this case, right?
Yeah.
Okay. So to answer your question, the reason why we do not want expression in the baseline. So let me first draw the baseline here. So this is the baseline without any optimization. So your question therefore becomes, so how is this one different from this one, right? Did I answer, do I understand your question correctly?
Yeah.
So as you can see in the baseline, the expression a plus b is evaluated twice along this program path, which is our definition for partial redundancy. Expression a plus b is evaluated twice, where it should not, right? There's no reason why we want to evaluate expression a plus b twice.
Okay, I see. In the right, you're only taking one path. You're not taking both paths.
Yes.
Okay. I see. I see.
Although one might argue, okay, so expression a plus, we have okay two expression a plus b here that might slightly increase the binary size. Okay, but I mean, so what? I mean, in most cases, people do not really care about the binary size, whereas register, as we have discussed, is the most valuable, one of the most valuable resources, our CPU. So therefore, we want to have as short register lifetime as possible, as we have shown here in the solution here. Yes, that's right. As you can see, this is sort of like a trade-off here. Larger band, slightly larger binary size versus long register lifetime. But I mean, in general, people will pick the solution here. Is this clear?
Yep.
Okay, so let us move on. So if there are no questions, let us move on. Again, so this is just what we are describing just now on the board. So based on this observation, the key idea that we have is that so we want to postpone the earliest, because previously we just described the earliest placement, right? Based on this observation that we have, the idea that we have is that so we want to postpone the earliest placement as much as we can. And another key observation that we make is that so an expression is called postponable if it is not used. Okay, we can no longer postpone the evaluation of an expression if it is used. However, if this is not the case, we can keep postponing it, right, until the program point where it is used. Based on this observation and key idea, we therefore come up with the definition for postponable expression, where we say an expression is said to be postponable at program point P if all passes leading to P have seen the earliest placement, but not a subsequent use of the expression. Based on the definition of the postponable expression, we therefore define the latest placement, where we have a very complicated formula for this. But if you think about this formulation, it's actually relatively simple here. So let me erase what we. Does anyone have any questions here? So if not, let me quickly erase this. So again, our fifth step, postponable expression. And step number 6, latest placement. Let us now define placeable. Let us now come up with this term, placeable. We say that so an expression is placeable at a certain time if it is equals to either it is the earliest placement, or on the other hand, it belongs to the postponable region. That is, so it sees the earliest placement but not a subsequent use of it. So this is what defined as placeable. Okay, so the latest placement of an expression, as we said, is that so it belongs to the placeable region. And either we see a use of the expression, or it's not acceptable to place it as one of the successors. Not placeable to successors. Is this clear to everyone? That is, so we said that the latest placement is a place. Of course, it has to belong to the placeable region, where we say it's either the earliest or the postponable point. The latest placement is either the place where we see a use of the expression, or the expression is no longer placeable to successors. As an example, suppose that we have a control flow graph that looks like this. Suppose that this is all the placeable region here. And further assume that so for some reason, the expression is not placeable here, starting from this point onwards. We said so it's not placeable to the successors, and therefore the latest placement for the expression is here. Is this clear to everyone about this formula? Well, that looks pretty complicated, but this is how it is interpreted. Okay, so let me quickly go through the examples that we had. So this simple example that we had. Let us now go back to this simple example now. Suppose that we have this control flow graph. We have a partial redundancy on the left program path. Let us now, again, so we follow the steps that we lay out here. But first, do the anticipated expression analysis. This is shown here. Let us now do the will be available expression analysis. Based on the anticipated expression analysis and the will be available expression analysis, we can clearly see that the earliest placement in this case is the top basic block. Okay. The reason is because so as by our definition, we said that so the earliest placement is a place where the expression is not anticipated, but will be available. Is anticipated, but not will be available. Therefore, the earliest placement in this case should be the region where it is marked as green in the anticipated expression, but purple in the case of will be available expression. Therefore, the earliest placement is the top basic block. Okay. As we have shown, so this solution is good for partial redundancy elimination, but it's not good enough. Let us now try to postpone the earliest placement as much as possible. Okay, so in the control flow graph here, I use the gray region to denote the places where the expression is not postponable, and use the black region to denote the place where it is. Because as we have discussed, the earliest placement is on the top basic block. The regions that sees this earliest placement, but not a subsequent use, is defined as postponable region. Okay. So therefore, this is why the postponable region is as shown here on the slide, shown in black. Okay. So let us consider the place that we have here on the right-hand side. So what is the latest placement in this case? Again, so if we consider the program path on the right-hand side, we'll see that, so recall that, so we define what placeable is as a place where it is the earliest placement where it belongs to the postponable region. Consider the bottom of the basic block here. Because the region clearly belongs to the placeable region, and it is not placeable to among its successors, which is here, because it is shown in gray. Therefore, the latest placement in this case on the right program path is the end of the basic block here. Any questions? So if there are no questions, so after the latest placement, we have our final step, which is called use expression. So this is exactly the same with the liveness analysis that we had, but it is just the expression version of it, or sanity check for liveness. Yeah, and finally, you have the final placement as the latest ending the use expression. I mean, this expression is just a sanity check. Okay, so let us now go back and turn back to everything that we have described today. So in today's tutorial, we discussed what is lazy code motion, in which, as we said, lazy code motion is to eliminate partial redundancy with minimum register usage. Okay, we said that the first pre-processing step is to use synthetic blocks to break the critical edges. The reason is because so they eliminate certain optimization opportunities. We start by doing the anticipated expression analysis and came up with this notion of anticipation frontier. However, we observe that we do not need to place expression at all frontier to make partial redundancy global, right? We only need to put on a place where the expression is anticipated, but not will be available. And this tool therefore gives us the earliest placement of the expression to make partial redundancy global. So this hence answers our first half of the question, eliminate partial redundancy. But however, as we have described, earliest placement is not the optimal solution to the partial redundancy elimination problem. We want to postpone the placement as much as we can. So when can we no longer postpone? We can no longer postpone until we see a use of the expression. Based on the earliest placement and postponable expression, this hence gives us the latest placement. And finally, we just have a use expression as a sanity check to make sure that the expression is indeed used in the program. Any questions here? regarding what we described today? So if there are no questions, that's everything I have for today's tutorial. If you have any questions or concerns regarding the midterm assignment 1 or 2, please feel free to leave and ask me. Otherwise, yeah, thank you so much, everyone. Any questions or concerns about what we described today, or the midterm or assignment 1 and 2?
I had a question for assignment 1.
Yes.
I had
So
had
if
the
you want to-
issue with.
Sorry, if you want to sorry for interrupting. If you want to discuss this privately, I can open a breakout room, or you're fine with discussing this publicly. I mean, it's up to you.
Yeah, it's a general question.
Okay, sure.
Just so the part that I couldn't get right was in the Fibonacci, I think it was the number of there's a number of instruction uses or something. There's like you know which one I'm talking about? Where we had to do a call, we had to cast it to a call instruction.
Mhm.
So what was like the logic behind that? Like, why didn't it work like the regular way, like just counting the number of instruction uses? What do we have to do different?
Okay, so the reason why you cannot simply count the number of uses is because it is possible for the function to be used, but it's just not an explicit call. For example, I can assign the function to a function pointer. That is a use of the function, but it is not an explicit call. Right. So therefore, as we have described during the tutorial, what you want to do is you first get the number of uses, which is good. And then after that, you want to make sure that the use actually belongs to an explicit call site. And therefore, you try to cast the use into a call instruction and see whether it indeed belongs to an explicit call site.
Okay. So I did try that. I know we discussed in the tutorial, but I couldn't get it to I don't know, maybe I was using the different types, but I couldn't cast it. Do you have the instruction? I mean, the assignment 1 is done now, but do you have the code that on how to cast it to a call instruction? I tried it and kept on saying incorrect type, like you can't cast it from a instruction to
Maybe
a.
well, I mean, it's shouldn't be the case because shouldn't be the case.
Yeah, I don't think you'll know, I'm guessing at the top of your head, what the line is, like the command is. Do you think I could email you just to get the line of code? Because I did, I don't know if I tried the correct one. I tried maybe something else, but it's call inst, right? CALLINST.
Depending on how the IR is translated, sorry, how it is translated into IR.
Okay.
Maybe checking the actual IR file, right? You know, so the generated IR file is located in your build directory when you run the test cases. So maybe checking the IR file to see whether it is casting to call instruction leads to failure.
Okay.
That's always the easiest way to check.
Okay, I see. And you do that within the for loop of the basic block, right? Like when you're going through the instructions, you said you go through the instructions, get the uses of the instructions, and then check if the use belongs to an explicit call. using call instruction.
No, it's as you traverse
So
through the function, so traverse through the function. For each function, you traverse through its uses and check whether the use.
okay. Okay, I see. Okay, sorry, I'm just taking notes. Function check if the use. Okay, yeah, because I just used the get num uses function on the for the number of calls.
Mhm.
Okay. Um, and what about the number of basic blocks? There was an error with that too. I think the number of basic blocks was 5, where I think I was getting 4 or something like that. Was there something fancy about that too? Like something different about that?
Um, the Fibonacci one. I remember the Fibonacci one is indeed 5, but I'm not too sure about that. I probably need to check. But uh, again, so you're saying the number of basic blocks is 5. Is it because when you check the C source file, it's 5?
Uh, I'm not sure. Okay, maybe I'll go through it again and I'll post a message on Piazza or something.
One thing that I'd like to remind you is that as we have mentioned in the handout, so it is important that when counting the number of basic blocks or anything that assignment, it is important that you check the actual generated IR assembly rather than the number of calls on the C side, right? As an example,
Yeah.
so in the case of Fibonacci, you'll probably notice that so the number of print is called twice, right? Rather than 3 times as it's shown on your C source file, right? Because the reason is because so LVM does some manipulation of your program. So that's when you actually see the IR file, the print function is invoked twice, right?
Okay. Okay, I
So
see. I
if,
see.
so yeah, so if you have any questions on and want to like let's say it does not really match your expectation, always make sure to check the IR file first.
Okay. Okay, cool. Okay, makes sense. Is there, and I had another question about one of the, I thought that, let me just open it up. I thought like lecture 4 or lecture 5, the professor kind of went really fast. uh, there were some things that were, what you covered today was basically a kind of a lecture 5 thing, right? Like,
Yes, I think let me check that.
okay, yeah. Okay, yeah,
Yes,
that makes
that's
more
right.
sense now.
That's right. So in the lecture this afternoon, we'll be covering register allocations.
Okay. And the midterm is covering this part? You said no, or
Up until lazy motion, because register allocations this afternoon won't be covered.
okay. So this lecture 5 will be covered on the midterm.
Yes,
Okay.
but not in the format as is assignment 2. Like we won't ask you to actually perform lazy motion, but it's mostly on the conceptual understanding. Like why do we need this? Exactly.
Okay. Okay. And the note also said we don't need to know, or like it's not covering loop invariant code motion.
Yes, that's right.
Okay. Okay. Great. Thank you.
Thanks. Hi, Luke and Kai Huan. Any questions or concerns about anything? Hi, Kai Huan. Do you have any questions or